gonna be implementing the computation of first and follow in C. This implementation will not use hash maps, it will only use arrays. We have to follow this algorithm um, to compute our first and follow sets. So let's first open up the editor. Alright, so we will be working on this example. Now I usually represent these production rules with this following convention. Let's first include our header files. Then I have to first mention the non-terminal characters, so which includes s over here. In this situation, only s is the non-terminal character. So then what we'll do is let's first define non-terms 3, actually it's 1, and we make a character array non-terms non-terms, character being s. Now we would like to have the corresponding production rules of each non-terminal. So let's make a character pointer array, which is basically a string array. And here what we do is we make prod rules, and then inside this actually it should be non-terms, there we go, non-terms equal to, so this is going to be our array, and inside this we're going to keep two strings. So the first string will be abs, and the second string will be asb. Let's see what the error is. Unexpected. Alright, so let me a semicolon. Yes, LMS, I think this should be 256 like that, because it's a 2D array. So this is just a limit as to how many production rules an array or a non-terminal can have. So I'll define it to be max prod rules. Let's set it to 256. Now we can go here and replace it to max prod rules. So let's first see if it compiles. This just gcc main.c o ff.exe. See if it compiles. Now let's just do that slash. Alright, it's working. Okay, so the first step in the algorithm, we first step in the algorithm is to first make our first sets for each non-terminal. There is only one non-terminal here, but we will write the algorithm such that it can accept more than one non-terminal. So reading through the algorithm, we can see that for each production A to alpha, do the first one. If alpha the terminal or epsilon, add alpha to first of A. Alpha is a non-terminal, add all symbols from first of alpha to first of A except epsilon. If epsilon is in first of A, continue to the next. So basically, I have, let's say that's a non-terminal, and I have alpha 1, alpha 2, and so on. Alpha n. Now if first of alpha 1 has epsilon, then find first. So let's change 1 to I. First of alpha has an epsilon, and find first of alpha I plus 1. Alright. If first of alpha I, alpha n has epsilon, add epsilon to first of this. So if has epsilon, add first alpha I to first of this, and find, and then add first of alpha n to first of this. Alright. So now let's do this. So first we need a dynamic array. I don't think we need a dynamic array because our number of non-terminals will not change. So then what we can do is we'll make a character array that's two-dimensional, and it will have first for each non-terms and how many characters. So let's define another variable. Define max first cars as 256. So now if I go here and say 256, and let's 0 initialize it. So that will have our first set for each non-terminal. Secondly, let's also make a for set num non-terms and 256 equal to 0. So these will have our first and follow sets for each non-terminal in our production rules. Alright. Now let's make a function called create first sets. Alright. Now we have to be iterating through each non-terminal and its production rules. So let's go here, size t I equals 0, I less than num non-terms, and then plus plus I. We also need a array that tells how many production rules does a single non-terminal have? So say num prod rules, and this is going to be num non-terms equal to 2. That's an array where the first element is 2 because the S non-terminal has two production rules. Two production rules. Alright. So now what we're gonna do, we're gonna initialize another array, initialize another variable. Let's see, ith prod rules equal to numprod rules of I. Alright. Okay, so now I'm going to say for size t. So we're going to iterate through each production rule. J equals 0, j less than ith num prod rules plus j. Alright, so let's start implementing. So j prod rule equal to prod rules I and j. Okay, and this should be a cast. So let's print this actually percentages backslash and just to see if our function works without any memory leaks. That's supposed to be printf. Alright, so let's compile and run this. So let's call create first sets and return 0. So let's compile and run this. I'm going to do this ./ff.exe, so it compiles and runs it automatically with a single command. So I think our code has worked. We have printed our production rule successfully, which means we are able to iterate through each production rules that we have in our problem statement. So that's good. Now we have to make our first sets. So let's follow the algorithm that we have over here. So initialize first set for each terminal. Alright, so we have a mistake over here. The first sets can be defined for terminals as well, not only non-terminals. So that means we have to find the number of distinct characters in our production rules, or we can just hard code it. Let's just hard code it directly here for now. So num distinct equal to, so let's see how much we have. S, we have A, and then we have B. So we only have 3 distinct characters. Now let's see, so this is supposed to be 3. Actually num distinct, this is supposed to be a hashtag define. Let's see. Alright, so this is supposed to be a hashtag define num distinct. Alright, and then num distinct. Alright, let's do the same over here. DIW insert mode num distinct. Alright, so we replaced our first and follow arrays with their correct sizes. Okay, so if it's a terminal, then the first set will contain itself. Alright, first let's do the step A. So we define a terminal as any character that is lowercase. Okay, this is our definition of the terminal character, but this is not a very good definition because a lowercase character can potentially define a production rule such as this. But in this case, by convention, we follow that terminals to be represented using lowercase characters. So that's why we assume this definition. So now moving on, let's find our terminal characters. So let's iterate through our production rule. So we can use strlen. Let's see, hash include str string dot hash actually. Let's see if it compiles. Okay, it does. Okay, so here what we do is we're gonna say we're gonna make an array, I mean a variable jet prod rule len equal to strlen of jet prod rule. Okay, so that's good. Now what we're going to do is going to iterate to the production rule itself. So for size t k equals 0, k less than jet prod rule n plus plus k. What we're going to do here is, so let's open up the ASCII table. Since we defined any small characters to be, any lowercase character to be a terminal, then we just have to find the range of terminal characters in the ASCII table. So let's open up the ASCII table real quick. So in the ASCII table we can see that lowercase characters start from 91, I think it's 61 or 91, I'm not sure. Let's see, this is 65. Okay, 97. So lowercase characters start from 97. So then what we're gonna do, we're gonna make a character array that holds current character, something like that. And then we're gonna jet production rule of k. So we are iterating through each character of our production rule, and on each iteration we store the character in memory. Alright, so let's make another function now. So let's make another function that returns a boolean, and for that I need to include boolean.h. I think it's in stdlib if I'm not mistaken. Yeah. Alright, it's in stdbool. stdbool.h. Yep, there we go. And here is lowercase. So given a character chr, it returns if the character is a lowercase character. Well, if it's a lowercase character, then its ASCII value must remain between 97 and 122. So we return ch 97 less or equal to chr. This will implicitly convert the character into its ASCII representation, so we don't have to worry about that. And chr less or equal to 122, and this should return true if we send in a or lowercase z, anything that is lowercase alphabetical character. So let's test this function. Let's go over here, let's call our function printf percentage d backslash n is lowercase, and let's send in a character such as g. We get answer 1 because it's lowercase. Let's check the edge cases. Let's see for z. Okay, 1 as expected, and a as well. Alright, so now let's send in a capital A, and it should print 0. I think I didn't save it. Alright, it prints 0. So that means our function is working. Okay, so now what we're gonna do is is lowercase and our character between being current car, then we have to add current car to the first set of itself, right? So let's see. So let's make a function called void add to first set. Alright, so for this function to work, we need a new array, and then we're going to size the first index. Okay, now say undistinct. No, I think only num distinct is enough. Yep. Okay. So what this will hold is it will hold all suitable insertable indices for the first sets, meaning let's say my array is empty, so that would mean my corresponding index for this array would be 0, which means I can insert an element at the 0th position. If it has elements 1 and 2, I can insert an element at the 2th position or 2nd position. I say 2th because the array is 0 indexed. So this is 0, this is 1, and I can insert another one at the 2nd index. Similarly, let's say my first set of this terminal S has one element, which means the next character in the first set I can insert will be at the first index. So that's the philosophy here. So initially this will be 0, and this will be 0 as well because both are empty. We need another index array over here. This thing is usually handled using dynamic arrays, but I don't want to define macros in this session, so let's just do this. So add to first set. Well, let's see. So we need the character to whose first set we will be adding. So let's make that character and let's call it parent, and let's make the character that we are going to add into the first set to be called child. Okay, very nice. So now what we do, is we first find the set for our parent, right? We first find the set for our parent. So let's see, how do we do that? Well, what we can do is let's call this first index as, let's call that first index as no, wait. So wait. Let's make an array here. Gonna be a character array distinct cars, and inside here we're gonna put our S, our A, and then on B. Okay, so this will have all our distinct characters and it should be non-distinct. Okay, so that's cool. So the first set of S would be at the index in the first array that is the same as the index in the distinct cars array, meaning the index of the S character here is 0. So the first set will be at first of 0, and inside that it will have the elements in the set. Okay, so let's see. So first what we do, we have to find our first index. So let's see. Size t first index equal to 0. Right. So let's say for size t I equals 0, I less than non-distinct plus I. If distinct cars of I equals our parent, then that means first index. So let's set it to -1 actually. First index equals I, and we'll break out of the loop. If for some reason first index remains as -1 equal to -1, then we'll simply return out of the loop because we do not want to cause undefined behavior. So let's run through this again. We have a distinct characters array and we want to find the index of our parent character. So if the character at this index is same as the parent, then the first index must be the index of the character itself. So that's what we do over here, and then we break out of the loop because we found our character. If first index equals -1, then we return. Alright, now to simplify this, let's just make a function called linear search. Actually this is supposed to be integer because size t can only accept values from 0 to int max, I think. I may be wrong, but it's a very big value, I remember it. So let's do a linear search. Let the linear search return an integer, which is the index. And here what we're gonna do, we're gonna find, let's make a character linear search. So needle, so what are the thing we're going to be finding, and star haystack, the thing we are going to find from. Right. So let's also make a new variable called haystack length. Okay, alright, so let's make an index variable, initialize it to -1, and then for size t I equals 0, I less than haystack length plus I. If haystack of I equals needle, then index equals I, break, and we simply return the index. So that's an implementation of linear search where the haystack and needle are related to the character data type. So that's good. Alright, so let's break out of that. Return our index. 1 minute. Return our index. Alright, cool. So now what we do, so let's just call this function now. So first index would just be linear search, and our needle is parent, haystack is I think distinct cars, and then or len is basically the macro we defined above, now distinct. Now if first index equal to -1, then we simply return from the function. Alright, then moving on, we need to add our child character to the first set. So that's what we need to do now. So first uh, since sets do not contain duplicates, we first check if character exists already. So let's first check if it exists already. So let's do boolean exists equal to, we'll initialize it to false. So we're assuming that the character does not exist in the set initially, and we will check if this is a false assumption or a true assumption and change it depending on whatever we find. So let's iterate again. st so now we're going to iterate through the set itself. So I equals 0, I less than. Now here is where we get this, we use this thing. So first index. So alright, so let's see here. So size t set len equal to first index. Right. So let's call this, we don't want naming collisions. Let's call this, let's make this first indexes in that same naming convention. First indexes, let's call it first, first up index. So up meaning append. So the index will hold the index where we can append a new one. So up indexes, yeah, first up indexes. So that's good. So now I can just say the first index, meaning the index of our first set, and set len. So this is where we do first app indexes of first index. So the variable, the position where you can append the variable is also the same as the number of elements in the list or set or any linear data structure. So we can use that value to avoid iterating and causing an overflow when iterating through the data structure, right? So let's do, fuck, I don't know how to copy, my bad guys. Control my thing, it's a p, yeah, p. Alright, so let's set n and then plus I. Alright, so now check if it exists. So actually what we can do is we can call this linear search. So since index is -1, if it's not found inside the haystack, then if our character that we give doesn't exist, then we should get -1 in return. Okay, so now that we have our set, then let's call that function. So if and we don't even need this actually, I don't even need that. So let's call our linear search. Let's call linear search. I don't know why I'm not getting code completion. Hello, what the fuck is happening? Let's restart the ID maybe. Let's try this. Okay, so I'm back. And when did I leave? I think I left it off here. Let's call linear search. So our needle is our child. Our haystack is first, our first index, and our haystack len is set len. So if equal not equal to -1, then that means it already exists, so we don't have to do anything else. Okay, so that's good. We can just return out of the function. If not, we have to actually insert our character, child character. So let's see. So what we do is we see, so first uh so let's say first set, so it's okay, type the set first set equal to first of first index. First of first, let's basically get an instance of that so it's easier to work with. uh First of first index, there we go. All right, sure, so that's good. Now first set. So now let's see. So the index where we're going to insert, we already have over here, which is set len. So all I have to do is first set of set len equal to child, right? But then now that we've inserted a new element, we have to update our first app indexes. So let's see. After we append our child, we go first app indexes, first index plus equal to 1. I know I'm using Python convention here, you can just do plus plus as well, but I like writing it explicitly like this because sometimes I catch myself in undefined behavior when using shorthand operators like plus plus. So I just like this convention more. Alright, so now that we have opened our set, our child to our set, we can safely return out of the function, which is done implicitly. We don't have to write return here because it's a void function. Alright, so let's go through. So we first find our first index. If our first index is invalid, then we simply return. We find how many characters our set already has, and then we search through our set and see if child already exists. If it does, then we simply return. If it, and since we return over here, we will only be here if our child exists and if first index was valid. So then let's take our first set. In first set we append our child and then we update the size of our first set. So that's essentially what's going on over here. Alright, cool. So now let's go back here. So if is lowercase, then we simply do let's see, add to first set, add to first set, and parent is current car and child is current car. Alright, so let's see if we have any bugs. So let's call create first set over here. Let's first see if we have any compilation errors. We don't, and it successfully ran, but let's verify our result. So first of A and B needs to have A and B itself because they are terminals. So let's check over here. So which array? I think it's first this one. We have to iterate through this one. So let's check. So first, yeah, we have to iterate through that. So let's see. For size t I equals 0, I less than what is the num distinct, right? And then plus plus I, and then so let's see, size t set len equal to first app indexes of I and our car star first set. So actually what's going on Is this safe to access? I don't know. I think it's safe as long as I don't treat it as a string, because strings usually end with a null character. But as you can see here, I'm not using a null character to end my first sets, because we don't represent it as a string, we represent it as a set of characters basically. So first set equal to first of I. Alright, so now let's iterate through our first sets. Actually, let's do car. Let's do car parent equal to num this non-distinct cars of I as well. Alright. So let's see. So let's first print our parent character percentage C with a colon and our parent. Alright, and then what do? For size d j equals 0, j less than num distinct. Actually, not num, it's actually set length. Let me charge my laptop real quick. So it's actually set length and then plus j. Okay, so now what we're gonna do is gonna say car child equal to first set of j. Right, first set of j, and we're gonna say printf percentage c with a space. Actually, let's just print c. That's better. And our child. Okay, and if j equal to setln, so not equal to setln minus 1, setln minus 1, then we just print a space so other characters can come after it and it will look nice. Alright, and after this we just do this, and that should be the algorithm to print our first sets. So let's run it. Alright, we see that A has A in its first set and B has B in its first set, because both are terminals, so that's good. It's working so far. So let's actually put this in a function called print first sets. So void print first sets will come into use later. So let's see. Alright, okay, so that's good. So now we can print our first sets whenever we want to verify our results. Okay, so first step in the algorithm has been done. Okay, so I'm gonna do is I'm gonna make this a boolean. So the reason we have to make this a boolean because I like to know if there was a new character that has been added to a set. So basically, if any set has changed, right? We need this because we iterate. We do this thing until there are no changes done, right? So we have to do this. Let's see. No, the no changes thing is only for follow sets. Alright, so for first set we are chilling, we don't have to do it. Okay, so let it be void then. So first step in the algorithm is done. So we added our first sets for non-terminals. I know this is a multi-pass algorithm and there is probably a more efficient implementation, but this is just to get the point across and will not be used in production. So if it was to be used in production, I would be using hash maps to prevent iterating for each um, terminal or non-terminal again and again. So yeah. Alright, so moving on, for each non-terminal A in G, initialize first of A as an empty set. We already did this because we zero initialized it over here. So first 0 and first element is 0. So this is basically just saying our first sets are empty at the start. For each production A, the following: if A is terminal or epsilon, add to first of A. Okay, all add symbols from first of alpha to first of A except, okay, fine. I think we do need it. Yeah, let's just make, I'm just being careful, so let's make it to do as, and this will return false, meaning nothing has changed, and this will return true. Alright, so that's done. My return false. Okay, so that's good. If is lowercase, and then just set uh, so make an array for bool changed equal to false, and just say changed equal to changed or this. Okay, so that's good. Okay, so do I actually let's set this to true. Yeah, true. I'll handle that later. I think I can just use a do while loop or something. Okay, so that's fine. So now what we're gonna do is gonna see wait for size t. Let's iterate through each distinct characters, right? Yeah, pretty sure each distinct character. No, each non-term, because we need our production rules, right? We need our production rules. So let's see. I less than now non-terms. Alright, I'll be back soon. Okay, we are back. So iterating through each production rule, I believe. So let's see. Non-terms and then plus I. Alright. So card parent. So let's see. So what we want to do is we need to do this. Yeah, repeat only no changes in process. I didn't see this line, but thankfully we updated our thing to boolean so we can track our changes. I think I can just do this to be fair, like that. Alright, and then bool changed and then equal to false. Actually, you can just do that, and then do. I think I need to go to visual block mode. Shift I. Alright. And then while change. Alright, that's good. Okay, so that's fine. Now parent is just going to be no, not no, it's going to be uh non-terms of yeah non, it's fucking not working again, bro. Alright, let's quit again. I think I'm doing something that I don't know and fucking myself up. Anyway, let's go back. Non-terms. Oh my. Okay, so let's see. So if it's a terminal, right, so we have to iterate through each production rule as well. We have to iterate through each production rule. So let's see how do we want to do this. how do we want to do this? First of all, I have to see which character mutates epsilon. I'm going to let it be dollar. Not dollar. Let it be ampersand. Okay. Let it be ampersand. So yeah. Alright. It should be fine. I don't think it'll be difficult. Okay, so let's iterate through each production rule. Size A, J equals 0, J less than non-prod rules of I, and then plus plus J. Okay, very cool. Say it's not prod rules. I don't know, J is prod rules maybe. No, wait. Yeah, yeah. Wait, just say ith non-prod rules equal to non-prod rules of I. And I can simply change it up like that. Right. Okay, that's good. So since TJ equals 0, J less than that thing. Okay, so now I can say cos star jth prod rule equal to prod rules of ij. Amazing. Alright, so a car first car equal to j prod rule of I. Okay, that's good. That's very good. Um, so if first car somehow turns out to be a null character, just continue. Okay, that's fine. Now this is our first car, right? So basically, what we need to do is we need to call some function called. Let's see. The function name should be. Let's check it out. Function name. Append sets. No. Combine union sets. And it should be destination. Source. Okay, that's fine. So union sets. Let's make it function calling it first sets. So yeah, let's go up all the way here, and then we're gonna say void union first sets, and inside here I'm gonna say car parent and car child. So child set will be unioned into parent set. Okay, that's good. Okay, fine. So that's fine. Now let's see. Alright, so int parent first index. So index of our parent's first set is gonna be linear search, and inside this we're gonna call our needle. Our needle is parent. Haystack is distinct cars, and haystack len is non-distinct. Okay, so that's good. Now let's parent first index. Let's do our child first index as well. Call linear search child. I think we can just copy and paste it and change it to child. Alright, cool. So now if parent first index equals -1, so if parent didn't exist in any character, or child first index equals -1, and we return. Okay, good. So now Let's see, car star parent first equal to first of parent first index, and car star child first equal to first of child first index. Alright. Um, so now we just have to union these two sets. Just have to union these two sets. So let's see. Let's make a function for union sets. So here, let's say star set 1, star set 2, size t, set 1 len, size t, set 2 len. Okay, so actually it should be destination. Destination and source. Okay. So let's see. No, we don't want this to, let's just do this. So first child, parent first, child first. Do we need parent first? I do not think we need that, so let's see. We just need this. Don't need that, and you do not need this. You do not need this. Okay, that's fine. Okay, that's all good. Very nice. Okay, fine. And now I'm gonna do for size t. So you have to see. So child first. Right. So size t, child set len equal to first app indexes of child first index. Alright, so for I equals 0, I less than child set len plus I. Okay, so here we're just gonna say add to first set, or parent being parent and our child in this case being, let's see, it should be child first of I. Okay, so that's good. So now let's call union first sets. Parent should be the parent, and our child should be, let's see, our child should just be first car, if I'm not mistaken. Alright, so that's good. This in and of itself should work because our production rules don't have any epsilons. However, we do not want to make a specific implementation. Alright. So let's first check now if the first set of first car has epsilon, then we have to continue, else we can break. So let's see. So let's make a function called bool has epsilon. Okay, has epsilon. Do we really have to? Yeah, let's see, has epsilon. So car parent, so the owner of the set. I think that's only enough, so that's cool. So let's say in first index is basically a linear search for parent, and haystack is distinct cars. Haystack len is non-distinct. Non-distinct. Okay, so that's our first index. Now we just have to see. Just have to do a linear search again. So return equal to not equal to -1. So it has epsilon. It should return -1. And basically, we're going to do a linear search here this time. Our needle is at symbol. At represents epsilon. It's basically first index, and this one should be first app indexes of first index, so that's good. Alright. Alright, so that's good. That's very cool. Okay. So union first sets. Here what we do is we're gonna say if has epsilon. So if let's just put so first card. So if it does not have epsilon, then we can just break. We can just break, right? Right now, yeah, we can just break. So if it doesn't have an epsilon, we don't have to check the other production rules. We can just get out of here. Right, if it does have an epsilon, then we have to check the following. Okay. So this condition is a bit strange because if has epsilon, let's make this has epsilon. If has epsilon, and if j equal to ith num prod rules -1, then we just need to add to first set parent, and then we need to add our epsilon. Else we don't do anything. Yeah, don't do anything. If it does, okay, so first of all, only this should, right, only add to first set. Only add to first set should affect our variable. So let's see. This is gonna be a boolean. It's gonna return false, and this is gonna be a changed bool change equal to false, and let's just say changed equal to changed or that. So once it becomes true, it will always be true, and return change. I think I need to do the same over here. Change or that. Okay. Alright, that's good. Now yesterday change changed equal to changed or this. Alright, and that's fine. Has epsilon add to first card, changed equal to change or that. That's fine. So else just break out of the loops. Okay, so that's fine. This should work. So union first set. So guys, I think that's it, to be fair. So let's just see over here. Print first sets. Let's just see. But mostly it won't work. Oh, it did work. So let's check if this is correct. So going all the way up, it's either ABS or ASP. Alright. ABS or ASB. So right. Mm, wouldn't we actually? I think there's a mistake in this algorithm. If A is turned on, okay, fine. Right. Okay, I fucked up. Okay, so basically, we're gonna have to iterate through the production rule itself. Alright, because the first character can go bye bye if the first character of the production rule can produce an epsilon. God damn, this is difficult than I imagine. Okay, a k less than strlen of jth power rule. No, what did I do over here then? I just did that. Alright, fine. Let's just copy this. Paste. Okay. Jth power. Let's close this. View. Show the stuff. Okay. So that's supposed to be jth prod root len. Okay, and then plus k. Alright, so here we do this and we do there. Yeah, the break goes in there, that's fine. And then we simply tab that in, and this should be k, I'm pretty sure. Right, I think that should be k. Yeah. Okay, continue if has epsilon. If it doesn't have epsilon, then we just break that. Okay, so this is a much better thing, so let's run it. So S has only A. Yeah, okay, that's good, that's correct. Fine. I think that's good. Yeah. Okay. So that's fine. So we got S is first set to be A. So this is working. I believe that is working. Okay. Alright, so it is working. It won't work for this example because B is notated as a capital letter but is actually a terminal. So yeah. Okay, fine. That's good. Let's see. Alright, so the first set creation is working. So that's good. Now we have to do follow sets. Okay, so that's good. So let's make a new function for printing our follow sets. So print follow sets are non-distinct. This should be follow and follow and follow. Parent settling. Yeah, that's fine. This should just be follow. Follow set. Okay, so that's a follow set print function. Now we just have to find our follow sets, and I think we should be fine. So I think we just copy this exact function So let's see. For each production rule, add all symbols from first of beta to follow of b, except epsilon. If beta is epsilon or the symbols in beta derive epsilon, add all symbols from follow of a to follow of b. Okay, fine. So this is easier when you convert the production rules to Chomsky normal form. I think, since we're not doing that here, we must do this. Okay, I think this thing should be easy. So add all symbols from first of B to follow of B. Add all symbols from follow of A to follow of B. Initialize follow set for the start symbol as a star. Okay, so I think you have to put dollar over here. So let's first do this. So follow. That's fine. I think. Just have to say follow app indexes of 0, which is a start symbol. I think I can just wait a minute. I think before anything starts, I can just call add to follow set. Right, I think I have to make an add to follow set function. Let's just make the follow params. So rule add to follow set, and I think I just copy this and just paste it here. So let's see here. Percentage s slash first follow slash g training characters. Wait a minute. Let me see. Find and replace check slash book. I think that's what I did, right? No, that's not working. Replace all foo with bar. I think I have to do. Oh, right. My bad. I think that's, yeah. First follow G. Oh my god, why is it not working? Slash percentage first follow. Where are the training characters? Let's see. First. Very weird. Follow didn't work. What a weird situation. I used to do it manually. Okay, so this should be follow, and that should be follow. Okay. This should be follow index. Follow and follow. Follow and follow. Wait, I fucked up. Follow index, right? Follow index. I think the same thing over here. Follow index. Okay, and follow set equal to follow or follow index and follow set again, and I think follow here, follow, right, and follow, yeah, what was the thing? Okay, so it was first index. I'll change it to follow index. Yeah, that should be fine. Okay, so first is first follow second search follow set len first set follow set first set len follow set len follow app indexes follow index plus equal to 1 to 10. Okay, that's fine. We need this function. So I was trying to do here add to follow set and parent is s and child is a dollar symbol, and that's step 1 of the algorithm. So let's just verify print follow sets everything is working correctly, and it is. That's good. So S has our dollar symbol that we want. Very nice. So that's good. That is good. Let's close this. Oh, I didn't mean to close the sheet. Um, let's see history. I think it should be, yeah, this one. Right. So so this is done. For each production rule where B is a non-terminal, B is a non-terminal. Really? Yeah, B. Yeah, fine. But here it's not really written like that, is it? See, D is not a non-terminal here. I guess you can compress it to this form. Well, I think it's fine anyway. So, add all symbols from first term beta. Okay, so let's first see. Let's just copy that. Maybe no, I'll just type it again manually. I think that's better. So, void create follow sets. Void create follow sets. And here, what we do is we basically, I think you can just copy all of this boilerplate. Right, I can just copy all of that boilerplate and just paste it here actually. Alright, so let's just start putting in our close brackets and then just do while change. Okay, so that's fine. That's our boilerplate, so that's good. Okay, that's fine. So all we do is we need to check if the last character of each production rule is a terminal or a non-terminal. Okay. Add all symbols from first of B to follow of B except epsilon. Now why except epsilon? Right, because if it's epsilon, then we have to add follow away. Right, it's an entire thing. We can fix it though. It's no issue. So okay. So I don't know why I put a gap over here. It's fine. Anyway. think it's a child. So child is basically a car child. Did I declare my parent? Don't think I did. So let's see. Parent, car parent actually. Parent equal to non-terms of I. And then child should be jth prod rule of jth prod rule n minus 1. Okay, so that's good. I think I should just call this last card, and for some reason if it's this, just put that. Okay, so that's good. So if last card is for some reason null character, then we will continue. Okay, so that's good. Now there can be two cases. One is if it's a terminal, so let's handle that case, is lowercase, and last card. So if it's a terminal, then we just union our sets. And let's see. So I'm gonna say boom. I think I wanna make it at the bottom. So boom union follow sets, right? Card pattern. So I think follow sets should have epsilon if I'm not mistaken. Add all symbols from follow of A to follow of B. Yeah, follow should not have epsilon. So I think this function should be able to ensure correctness. So that's cool. So int child follow index equal to a linear search for child in distinct cars and num distinct. Okay, so if child follow index equal to -1, then we return false. Else we make a variable called changed, then car star child follow equal to follow of child follow index. That's supposed to be square brackets. So alright, and then child set len. So size t child set len equal to follows app indexes of child follow index. Alright, so if we're just going to iterate, so I'm just going to return change, that's fine. Then for size t I equals 0, I less than child set len, and then plus I. Okay, so if a child first of I not equal to ampersand, so if it's not epsilon, then we just say change equal to change or add to follow set, parent being our parent and child is child first of I. Okay, so we have some errors here. Let's see. Oh yeah, it's supposed to be child follow. Wait, child follow and child follow. Okay, That's good. Fine. Very good. So union follow sets is done. Okay. So what we can do is if is lower character. So actually we have to take first set and put it in the follow set. Right. So let's see. How do I want to do this? How do I want to do this? So union for follow sets, and just copy this, put it right there. Union follow first set. So this is supposed to be first, and first, child first, and child first, and this is supposed to be first. Okay, so far so good. Child set len is first app indices with child first index being right there, and then child follow is actually child first. Okay, and then child first, child first. Okay, that's good. That's fine. Very good. So union child follow and follow sets is fine. Union follow first sets is also fine. Okay. That's fine. That's fine. So since only five. Wait, what the fuck? My bad, my bad. So since only um, first sets can contain epsilon, I don't need that there. So union follow first sets, and follow meaning for parent, first meaning for child. So I think this is fine. Child first, child first. Okay, that's good. So let's just call it. So change equal to change on union follow first and parent and last car. Alright, so let's compile and run. So far nothing has happened, huh? That's weird. Oh, it's because I didn't call the function. So let's see, create follow sets. Let's call it create follow sets. Let's check. Okay, so we got dollar and b, so let's check. I think we got ASB, ABS, and ASP. Okay, so I think that's fine. So I just have to add a case for this. Okay, so that's good. Um, First in the, I think this is fine. Child first up, child settling, first app. Okay, child first up. I had to follow set. Okay, I think it should be fine. Okay, so now I just have to handle this other case. Meaning if it's a terminal character, but before that we have to handle this. So if b is epsilon, or the symbols in b derive epsilon, we have to handle this as well. So let's handle that. Follow of a to follow of b. Okay. Let's check. If b is epsilon, or the symbols in b beta derive. Okay, so that's fine. Let's see. So this is the last character. So what is bits before the last character is the question. It's the question. Hmm. Let's see. Hmm. Let's handle this first of all. I think that should be fine. Change equal to changed. Or union follow sets. Parent comma last car. So if the ending is a terminal or whatever, I mean non-terminal, then we do this. So we handled this part and we handled this part. So if b is epsilon, then we handled, actually it should be, yeah, it should be child last car, and last car is the destination. So should be, so follow add as a follow a to follow b. So similarly, to last car follow set, we add parent follow set. So now we just have to find a way to handle the situation um, where the last car derives epsilon. Last car derives epsilon. So let's do that. So if jth prod rule n minus 2 greater than or equal to 0, first of all we must figure out if beta is okay. I don't think we gotta do that, right? Yeah, what am I doing? Let's just check it out. 1 minute. Yeah, so if has eps and last car, so that means last car can derive epsilon. Last car can derive epsilon, and if I jet, I think I can just put that here. No, it's fine. If j prod rule n minus 2 greater than or equal to 0, and is not lowercase, is lowercase, jth, I don't know, man. Control R, let's just, I know it's very difficult to read the code, but I think this maintains my sanity when I'm writing the code. So car last previous to last car equal to jth prod rule of jth prod rule n minus 2, and if it's a non-terminal, so if is lowercase for our I think, yeah, fuck. Alright, let's see, is lowercase, so that's one of the, it should just call this thing is terminal or something. Or chr equal to that. I'll just do that. Okay, fine. Where the hell was I writing my code in? So if it's not a lowercase, then we just have to do this. Change equal to changed, or union follow sets, and that being pre last car and parent. Okay, that should be the algorithm. So let's run that shit. Okay, think it's fine. Think it's working. So first away is a first of S is also A. First of B is B, and follow of S should be B. Right, follow of it should be B. Yep. Okay, so it's working. That's the implementation. So I think that's fine. So yep, let's just see. So if not is lowercase for parent, only then we will print the follow sets, because only non-terminals have follow sets. So very nice. So I can just do this and let's make it prettier. So printf first sets \n, and also print \n over there. No, I don't think it's fine. I think it's fine. And then print follow sets \n, and then print f. I think that's fine as well. So all I have to do is put this, and if I run this, I should get that, and that's fine. All right, thank you very much for watching. I will see you later.